Question 4.4 is the last one we're going to go through for this lecture. Shows us two discs, and these two discs are rotating, and the key part of the question is that it says assume that there is no relative motion between these discs at their point of contact. So that means that this disc, which is rotating clockwise, the green arrow tells you the direction of the, it's anti-clockwise. The yellow arrow tells you the angular velocity, so it's rotating in this direction. But because there's no slip between the two discs, it means that this bigger disc is rotating in the opposite direction. So they'll be doing this sort of thing. So it tells you what the angular velocity and the angular acceleration of the small disc are in the question. The first part, so part A, asks what is the angular velocity and the angular acceleration of the larger disc. So I'm just going to draw a quick sketch. There we go, two perfectly circular discs. Those are the fixed axes. Now there's quite a lot of detail, maybe I should have drawn it slightly bigger. This is, I won't write point A, I won't draw point A yet because that's only relevant to part 2 of the question. The diameter of this disc is 2.5 meters. The diameter of this disc is only 1 meter. And the important thing to realise is that so let's just draw the angular velocities first of all. So you've got an angular velocity of 3 radians per second. So that means that there is a tangential velocity in this direction. So that's Vt. And because there's no slip, it's got to be common to both of these discs. So the tangential velocity at this point of the left-hand disc has got to be equal to the tangential velocity at this point of the right-hand disc. So we know from our lecture notes, if we go here, that the tangential component of velocity is equal to r omega. So omega, our angular velocity, is 3 radians per second, and r for the small disc, so let's call this one, let's call this disc J, and we'll call this disc K. I would call them A and B, but we've got a point B later in the question. Okay, so that's J and that's K. Now, the radius of disc J is given to us as 1 meter, and this is the angular velocity of disc J. So the tangential velocity, Vt, is equal to omega J times Rj. So that's just that expression there. I normally put R first. And we know that that has got to equal 3 times 1, so that's 3 meters per second. But that has also got to equal the tangential velocity of disc K. So that means the angular velocity of disc K times the radius of disc K has also got to equal 3 meters per second. Because we know Rk, we can rearrange this. So our angular velocity of K is equal to 3 divided by, and Rk is 2.5. That's the radius of disc K. And that 3 divided by 2.5 is equal to 1.2 radians per second. So, and we know that that is in this direction, so it's going in a clockwise direction, 1.2 radians per second. So that sort of makes sense because the larger disc is rotating slower than the smaller disc, so it's geared down. and that's the answer to the first part of part A. It also asks us to find out what the angular acceleration, and this bit might not be quite so intuitive, but it's essentially the same as the first bit. So we've now got let's draw a different colour. Now got an angular acceleration. Let me draw it this way. This is going clockwise, and this is 3 radians per second. No, 1 radian per second squared. So we're going to have a tangential component of acceleration in this direction, and again, because could be no slipping, if the velocity is the same, then the tangential acceleration has got to be the same at those 2 points as well. Otherwise, the velocities would become out of sync. So that means that we can use essentially the same approach here. Go to our lecture notes. The tangential component of acceleration, AT, is equal to Rj times alpha j. So that's the radius of the disk j, which is 1, times the angular acceleration of disk A, which is also 1. So that's 1 meter per second squared. And that has got to be equal to the same, but evaluated on the larger disk. So the radius of the large disk is 2.5, and we're trying to work out what the angular acceleration of that is. So if you rearrange this, that's equal to 1 meter per second squared. Then you can see that the angular acceleration of disk K is going to equal to 1 over 2.5. 1 over 2.5, 0.4. Yeah. Oops, another bit of space, 0.4, and this is radians per second squared. So that's the second part. It's going to be, if we just draw the direction in, that's going to be in a counterclockwise sense, so that's 0.4 radians per second squared. So the second part of the question is then, given that you now know the angular velocity and the angular acceleration of this disk, what are the velocity magnitudes at some distance, velocity and acceleration magnitudes at some distance away from the centre, and actually it's given to us as 2 meters. So this is identical to 4.1 and 4.2. What we did there, we calculated the components of velocity and A, and the components of acceleration at A, and from that calculate the magnitude. So I'll do that quickly and refer you back to the earlier example if you don't quite follow what's going on, but there's a tangential component at A. So I'm just referring to it, this is all at A now. At A. So the tangential component is equal to R times omega of K, obviously. So it's 2 meters here, multiplied by 1.2 equals 2.4 meters per second. And that is the tangential component and also the magnitude of velocity at A. Now there are 2 components to acceleration. You've got a radial component, which is equal to R omega squared. That is equal to 2 times 1.2 squared, 2.88 meters per second squared. And you've also got a tangential component, which is equal to r times alpha k. So so 2 times the angular acceleration we calculated here times 0.4. So that's equal to 0.8 meters per second squared. So the magnitude of acceleration we can obtain from Pythagoras, because we've got the two components, which is equal to 2.88 square root of 2.88 squared plus 0.8 squared, which is something not quite right there. Did I calculate the 1 second? I think I might have calculated this wrong. That should be 2 times 1.2 squared. 2.8. No, it's fine. Okay. So that gives us a value of 2.99 rounds up to 3, but yeah, 2 meters per second squared. And I think that's the right answer. Yeah. Okay.